I would like to welcome you all to today's lecture about NEAT. Today's topic will be about evolving neural networks through augmented topologies. Well, let's start then. Neuroevolution, the artificial evolution of neural networks using genetic algorithms, has shown great promise in complex reinforcement learning tasks. Past studies have shown neuroevolution to be faster and more efficient than reinforcement learning methods such as adaptive, heuristic, critic, and Q-learning. This increased efficiency is due to three factors. First, the principled method of crossover of different topologies has been employed. Secondly, structural innovation can be protected using speciation. And thirdly, we start from minimal structure. There are many reinforcement learning tasks where the techniques employed in NEAT can make a difference. Many of these potential applications, like robot navigation or game playing, are open problems where evaluation is difficult. Within this presentation, we focus on the pole balancing domain because it has been used as a reinforcement learning benchmark for over 30 years. Here we got a nice reinforcement learning simulation by Tyler Streeter. This learning simulation is based on reinforcement signals, which are -1 when the pole falls over or the cart goes off the edge of the platform, +1 otherwise. Based on those simple reinforcement signals, the agent learns to balance the poles for 30 minutes after about 600 trials. Let us start this lecture with a small definition on neuroevolution. It is actually a form of machine learning that uses evolutionary algorithms to train artificial neural networks. Evolutionary algorithm means genetic algorithms. They were invented to mimic some of the processes observed in natural evolution. In traditional neuroevolutionary approaches, a topology is chosen for the evolving networks before the experiment begins. Usually, the network topology is a single hidden layer of neurons, with each hidden neuron connected to every network input and every network output. Evolution searches the space of connection weights of this fully connected topology by allowing high-performing networks to reproduce. Thus, the goal of fixed topology neuroevolution is to optimize the connection weights that determine the functionality of a network. So now we know that connection weights are not the only aspect of neural networks that contribute to their behavior. Topology or structure of neural networks also affects their functionality. Many systems have been developed over the last decade that involve both neural network topologies and weights. One design is called TOWEIN. This abbreviation stands for Topology and Weight Evolving Artificial Neural Networks. The simplest implementation is based on the traditional bit string representation, which is used by genetic algorithms. This encoding scheme is called binary encoding. Further encoding schemes are graph encoding, non-mating encoding, and indirect encoding. But right now, we don't want to get into detail. One of the main problems of neuroevolution is the competing conventions problem, also known as the permutations problem. Competing convention means having more than one way to express a solution to a weight optimization problem with a neural network. When genomes representing the same solution do not have the same encoding, crossover is likely to produce damaged offspring. Let us have a look at this figure here. This figure depicts the problem for a simple 3 hidden unit network. The 3 hidden neurons A, B, and C can represent the same general solution in 3 faculty. This means that we have 6 permutations. When one of these permutations crosses over with another, critical information is likely to be lost. For example, crossing A, B, C and C, B, A can result in C, B, C. We have a representation that has lost 1/3 of the information that both of the parents had. In general, for n hidden units, there are n faculty functionally equivalent solutions. So what is actually the main intuition behind our NEAT concept? This concept has been designed to take advantage of structure as a way of minimizing the dimensionality of the search space of connection weights. If structure is evolved such that topologies are minimized and grown incrementally, then significant performance gains will result. So the goal is not to minimize only the final product, but all intermediate networks along the way as well. Let's have a look now at this cursive sentence. It says that NEAT method of evolving artificial neural networks combines the usual search for appropriate network weights with complexification of the network structure. It's basically saying that the neat method is including both weighting and topology. Please keep that in mind. Further, evolving structure incrementally presents several technical challenges. Those challenges are listed here. We need to ask ourselves if there is a genetic representation that allows disparate technologies to cross over in a meaningful way. Secondly, we ask, how can topological innovation that needs a few generations to optimize be protected so that it does not disappear from the population prematurely? And thirdly, how can topologies be minimized throughout evolution so the most efficient solutions will be discovered? For all these three challenges already, solutions have been proposed. For the first challenge, the solution is to use historical markings to line up genes with the same origin. The solution for the second challenge would be to separate each innovation into different species. And solution number 3 would be to start from a minimal structure and add nodes and connections incrementally. And now, in order to make you understand the terms used in neuroevolution, which are genotypes and phenotypes, we will look first at the biological pendant. We want to clarify the signification of genotypes and phenotypes. In this orange matrix on the left, we have 4 different combinations. Upper B stands for that the chromosome is dominant and lowercase b that it is recessive. So we have a probability of only 25% that the child will have blue eyes, but a probability of 75% that it will have brown eyes. So what a phenotype is, it is the optical appearance. If somebody has in the end blue eyes or brown eyes, which is the result. And genotypes would be the biological chromosome which are either dominant or recessive. Here we can see a genotype to phenotype mapping example. The genotype are the node genes and the connection genes. The phenotype is represented by the network. Each connection gene consists of an innovation number. We will clarify later what that means. Other attributes of the connection genes are the number of the input and output node, the weight number, and a field which gives informations if a connection is enabled or disabled. This becomes important when adding or removing nodes. This is how it looks like when we have structural mutations. Mutation in need can change both connection weights and network structures. Structural mutations occur in 2 ways. Each mutation expands the size of the genome by adding genes. In this case, adding a connection is really simple. We just say what is the input and what is the output node. In this case, it's 3 and 5. Adding a node is a bit quite complicated. We need to add 2 new connections, one from 3 to 6, the other from 6 to 4. And we need to disable the connection with the number 3, which goes from the input node number 3 to 4. So the old connection is disabled and 2 new connections are added to the genome. This method of adding nodes was chosen in order to integrate new nodes immediately into the network. Through mutation, the genomes in need will gradually get larger. Genomes of varying sizes will result, sometimes even with completely different connections at the same positions. But how can neuroevolution cross them over in a sensible way? The next section explains how need addresses this problem. It turns out that there is unexploited information in evolution that tells us exactly which genes match up with which genes between any individuals in topologically diverse population. 2 genes with the same historical origin must represent the same structure. Another good thing is that tracking the historical origins requires very little computation. Wherever a new gene appears, a global innovation number is incremented and assigned to that gene. The innovation numbers thus represent a chronology of the appearance of every gene in the system. As an example, let us say the 2 mutations in this figure occurred one after another in the system. In the future, whenever these genomes mate, the offspring will inherit the same innovation numbers on each gene. Innovation numbers are never changed. Thus, the historical origin of every gene in the system is known throughout evolution. The historical markings give need a powerful new capability, effectively avoiding the problem of competing conventions. When crossing over, the genes in both genomes with the same innovation number are lined up. These genes are called matching genes. Genes that do not match are either disjoint or excess, depending on whether they occur within or outside the range of the other parent's innovation numbers. Let's switch to our next slide, which is about protection innovation through speciation. Speciation allows organisms to compete primarily within their own niches instead of with the population at large. This way, topological innovations are protected in a new niche where they have time to optimize their structure through competition within the niche. The idea is to divide the population into species such that similar topologies are in the same species. This task appears to be a topology matching problem. However, it again turns out that historical markings offer a more efficient solution. The number of excess and disjoint genes between a pair of genomes is a natural measure of their compatibility. The more disjoint two genomes are, the less evolutionary history they share, and thus the less compatible they are. Therefore, we can measure the compatibility distance delta of different structures in need as a simple linear combination of the numbers of excess and disjoint genes, as well as the average weight differences of matching genes. The symbol therefore is W dash. The coefficients C1, C2 and C3 allow us to adjust the importance of the three factors. Now let us switch one slide further. In contrast, need biases the search towards minimal dimensional spaces by starting out with a uniform population of networks with 0 hidden nodes. This means all inputs are connected directly to the outputs. New structure is introduced incrementally as structural mutations occur, and only those structures survive that are founded to be useful through fitness evolution. Since the population starts minimally, the dimensionality of the search space is minimized. So how can we apply need in a reinforcement learning task? Let's have a look at the following example. We got our student Liam, who is standing in front of the cafeteria and he's really hungry. But he should go to the exercise, so he has to decide. The reward will be -1 because of the hunger if he decides to stand or to go to the exercise. If he goes to the cafeteria, we will reward him with 10 points because the food is good. Otherwise, the reward would be 0 points if he decides to go to the exercise. The problem is, if he writes the exam and he fails, the reward will be -100. If he passes, it will be +100. So if he decides to go to the cafeteria, the probability gets higher that he fails the exam. Do you see the problem in this example? It is difficult to make predictions, but our agent, in this case the student, is capable of learning. And therefore we need machine learning algorithms, such as our need approach. We can improve our neural networks of agents by mutation or crossovers. Mutations occur by coincidence, for example when connection weights change, or new connections are added, or new nodes are added. Another possibility that we learned in this presentation is the crossover of two fit agents. They substitute a non-fit agent. Well, the problem is that the neural networks have different topologies, and therefore we have one solution. It is to use innovation numbers. Those innovation numbers are really useful because the agents can be classified into species which can cross over with each other in order to take care of new possible innovations. Now we have come to the last slide of this presentation. This is a short summary of our need concept. We have argued that needs performance is due to historical markings, speciation and incremental growth from minimal structure. In this figure here we can see the dependencies among need components. Strong interdependencies can be identified among the different components of need. I would like to thank you for your kind attention.